thing about a minute of what I actually did, or like the whole full 10-minute thing where I'm going through the entire project?
Oh,
That's a lot.
We would love 10 minutes that you'll like abusing.
it just feels like we will be like abusive.
Alright, well, you know what? I'll just start going and see what happens. So
Okay.
So are you recording?
Yes.
So in my research this year, I set out to maximize the thermodynamic solubility of carbon nanotubes. And in the process, I discovered a new method for maximizing solubilities in general through a fundamental connection I uncovered between solubility and the actual surface tension of the solvent. And this method lets you systematically mix different solvents together to reach an optimal surface tension that then maximizes solubility. So using this method, I was able to discover a solvent mix that dissolved over 10 times more nanotubes than the previous best solvent. And I was also able to show excitingly that my method can be extended beyond nanotubes, and I dissolved graphene and cellulose nanocrystals for the first time ever. Now, the reason dissolving these nanoparticles and maximizing their solubilities is so important is that these nanoparticles only exhibit their extraordinary properties in a thermodynamically dissolved form. So in my research last year, I proved that carbon nanotubes are actually thermodynamically soluble in this N-methyl 2-pyrrolidone solvent, or NMP. But the problem remained that NMP could only dissolve a very small amount of nanotubes, and was therefore still not truly practical for real applications. So that's why this year I tried to first understand and then maximize nanotube solubility. So I guess I can just tell you a little about about the theory, and then about some of the actual experiments I did. Okay. Well, so to quantify thermodynamic solubility, I used this property called the Flory-Huggins parameter, or chi, which can be experimentally determined through a static light scattering experiment that I devised last year. And generally speaking, by the laws of thermodynamics, this chi has to be negative for a compound to be thermodynamically soluble. So the more negative chi is, the more soluble the compound is.
Yes.
So to maximize solubility, I started with this approximate thermodynamic equation, which says that this chi is minimized when the Hildebrand solubility parameters, these variables here, of the solvent and solute match each other. So when these variables are equal to each other, solubility is maximized.
Oh, okay.
But I reasoned that because the actual surface tension of a solvent is theoretically related to this Hildebrand parameter, that maybe I could maximize nanotube solubility by first understanding the relationship between chi and solvent surface tension to make chi as negative as possible. And so my first step was to make samples of nanotubes in various different solvents and run them through the ultra-sensitive static light scattering spectrometer that I built.
Is the one you built, right?
Yeah.
Right, that was from last year's project. And this year, though, I added an auto sampler to my instrument so that I could quickly run hundreds of samples.
Oh.
And so I then plotted the calculated chi's, the Flory-Huggins parameter, versus the different solvents' surface tensions, and I was surprised to see what looked like this negative peak in chi centered around the data point for NMP. And so to try to clarify this peak, I searched for a long time for any similar solvent molecules with surface tensions around NMPs, but this was the big problem. I couldn't find any. And so I decided to several big data points around this peak.
Okay.
So when I then plotted the chi's for these mixes, amazingly, this much deeper true negative peak appeared, which was centered around the surface tension of 38.4 millijoules per meter squared. And the chi for the mix at the tip of this peak was over twice as negative as the chi for NMP. So, to try to verify this peak, I mixed different solvent combinations. And when I plotted chi versus surface tension, these new peaks appeared, which were centered around the exact same surface tension, but had various depths. And so then, to try to understand what controlled how deep the peak went, I decided to calculate this chi for a series of slightly different pyrrolidone solvents. So solvents all in the same family of molecules, but that differed in the number of carbon atoms in their side chain. And so, excitingly, one of these molecules was this cyclohexylpyrrolidone, or CHP. And I was amazed to find that it had a chi that was almost 5 times as negative as NMP. And so I was so excited, I right away measured the CHP's surface tension and mixed in small amounts of another very similar solvent, an ethylpyrrolidone, or an EP, to reach this peak at 38.4 millijoules per meter squared. And it was this new solvent mix that dissolved over 10 times more nanotubes than the original NMP solvent. So, just quickly I'll go through some of this molecular modeling I did.
Yes.
Because after making this discovery of CHP, I wanted to understand why it was so much better than all the other solvents. And so I decided to use the molecular modeling program HyperChem. And I built several different types of virtual models. And completely unexpectedly, I discovered that all the CHP molecules stacked together in a tight ring around the nanotube surface, with all the molecules' polar amide regions, their carbonyl group, these red oxygen atoms here, pointing in towards the nanotube, and all the non-polar cyclohexyl rings pointing outwards. And this strong ordering, this packing of the solvent molecules did not occur when I built the corresponding models for the other solvents, which explained why the CHP was so much better. And so the next thing I wondered was whether my solvent mixing method could be extended beyond nanotubes to other nanoparticles. And so I tried it first with graphene and then with cellulose nanocrystals, which, like nanotubes, have been universally assumed to be thermodynamically insoluble. And so I was thrilled to find that chi for graphene in CHP was actually negative, which proved for the first time that graphene is thermodynamically soluble. And I then constructed this peak for graphene, applying my method and mixing cyclohexylpyrrolidone, CHP, and NMP. And this peak had a chi that was twice as negative as the chi for just pure CHP alone. And so then, applying my method to the cellulose nanocrystals, I was able to very efficiently, in just about 2 weeks, zoom in on a peak for the nanocrystals by mixing NMP and DMSO. And what's interesting is that the pure NMP and the pure DMSO solvents on their own could not dissolve the nanocrystals. And it was only when I used my method and mixed the two solvents together that chi became negative.
Why? Why is that?
Why is what?
Why does why when they combine together they are soluble and
when you
independent?
combine the two solvents, mixing two solvents together, you reach a surface tension that's in between these two solvents. And if you mix the solvents in just the right ratio, you then reach this optimal surface tension, this special surface tension that actually matches the intrinsic surface energy of the nanoparticle you're trying to dissolve. And when you can match the surface energy of the nanoparticle with the surface tension of the solvent mix, you can then maximize solubility.
Oh.
And so these peaks for graphene and CHP, or graphene and then the cellulose nanocrystals, suggest that my method works not only for the nanotubes, but can be extended to maximizing the solubilities of materials in general. And also, because this method fundamentally maximizes the intermolecular interactions in a system, it could also possibly be extended even beyond this to maximizing the strength and stability of composite materials. And so finally, these enhanced solvents I discovered for dissolving carbon nanotubes, and now for the first time graphene and cellulose nanocrystals, could be the key to finally being able to apply these nanoparticles as supermaterials.
Okay, thank you very much. But I'm not familiar with the applications, because I think you didn't talk about the applications of the nanotubes.
Okay, sure.
So can you explain it a little bit?
Well, the applications, of course, after the key step of dissolving the nanoparticles, which then gets the nanoparticles into their individually isolated form. Because remember, for example, with nanotubes, nanotubes bundle together into these tight bundles which are weak and non-conductive and cannot be used in applications.
Oh, okay.
So, by being able to dissolve the nanotubes and these other nanoparticles, that means the individual nanotubes, for example, will be homogeneously distributed throughout your solution in their true individually isolated form with their super properties intact. So then you could then use those nanotubes that are spread throughout the solution to then build a polymer composite, for example, or actually apply them and combine them with other materials.
Oh, okay, I get it. Well, thank you very much. It's really interesting. I mean,
Amazing.
it's really amazing that you can actually do this by your own. I mean, it's really amazing. And are you going to continue your work?
Yep, I'm officially still a junior, so I'll have one more year, and I definitely am going to continue this research and working at the university where I live, the University of Wisconsin-Platteville.
Oh, how long do you think it's going to take for mankind to actually develop an application for nanotubes?
Well, the bridge to the moon is probably pretty far off, but the nanotube composite materials, just ultra strong yet ultra lightweight materials, are going to be very, very quickly produced, maybe in the next few years.
The next few years. Okay. Well, thank you very much for the explanation. I think it was really clear, and well, you can come see us through our E77. And what's yours?
EM52.
Look, I don't know if we have any time left. It's 2:15, but maybe we should go right now.
Oh, let's go. Yeah, before they close.
Before they close.
Can we get an abstract?
Oh yeah. Yeah, can I have an abstract?
Thank you.
Thank you.
It's really amazing.
Good job.
Oh my god.
Tranquilo.
Uh-oh. Hello?
Ya deja de grabar.
I can't. Oh.